Okay, section 4 of the waves chapter, that's chapter 9, takes us into a change. We are not looking at refraction anymore, we're actually looking at reflection, but actually we're not. So what we're going to look at in this chapter, or this section, is total internal reflection. Okay, so it's not refraction, but actually it is all about the idea of not light going into a substance, but actually not light not being able to get out of a substance. Okay, so TIR, as I will call it, use the title in the exam, the full title, but total internal reflection is what happens when you're inside a substance. So if you go back to last chapter, last section, we looked at the definition of refraction. From that, we went through the idea of the proof and the reason why that changes direction, and it's the idea that it's to do with the ratio of speeds, which were over here. And so from that, we get a powerful calculation. Formula or equation, however you want to say it, that will get us any answer to do with light coming into, changing direction, etc. However, total internal reflection is a bit different, and this is the idea that goes with the second video on the second part of the experiment. Sometimes if you're inside a substance, you find that instead of actually being able to escape out, the ray gets trapped inside. Okay, now it depends on several crucial factors, and that's where this comes in. But it basically comes down to two factors. All about the angle that it hits the surface at, so the angle from the normal, or which material it's in. So it's changing these variables in here. So let's come up with the main thing. First thing that a lot of people get a little bit confused with is they get really stuck on this, hung up on this diagram. Okay, here we have a ray coming out of a substance, and the substance, the first substance, so I'll reverse the order here. So substance 1 has a refractive index 1. If you reach a certain point, it can trap inside. Now, let's be very careful. You can always see reflected light. Okay, you can see a reflection of shadow here from light. Okay, so whatever the surface is, we can always see reflection. We've got a little bit down there in the background, yeah? However, some of the energy going down here goes into this plastic wrapper and through the other side, and it gets absorbed by the substance underneath, gets absorbed by the book. So, materials will always absorb some energy, but actually you'll always get some being reflected off. We're not talking about that. We are talking about the fact that if you happen to be inside a dense material, when you try and look out of it, instead of seeing all the way around from surface to surface, your whole life is squeezed into a cone. So if you're a fish, or next time you're at Barnsley Metrodome swimming around underneath the water, if you look up, apart from the splashiness, so a lot of wobbling around, you'll see a lot of silver, and then you'll see effectively a circle, and then within that circle you'll see everything that's on the outside of the pool, above the water level. So it's about being stuck inside a dense material, and what that does is leads into a whole world of different things, but a lot of people keep thinking about this. I'm going to stick away from that. The idea is that light will normally come out of a substance, but if it's coming out of a substance into a thinner media, then you will always find a bigger angle on the outside. Now, when that goes round and round and round, there is a maximum angle that can reach, and that's 90 degrees. To do that, this ray, the red ray, has to spin around more and more and more. Okay, so there'll be a point at which that ray no longer escapes. And as soon as you go beyond that critical point, any angle bigger than that critical angle, that certain value, it'll stay trapped inside. Okay, and that certain angle all depends on the speed of this material and the speed of light in that material. So it depends on both of them. Okay, and this is where, again, this calculation is great at working it out. Okay, so this is a bit of a dodgy diagram. It's not true as such, but again, exam boards kind of use that idea. So at the critical angle, it's not escaping, it's not reflecting, it's in between. What you'll find is that will often split up into a whole range of colours anyway, so you can't really tell. Okay, so have a think about that. Just try and make sure you get that sorted in your head. At the critical angle, greater than the critical angle, so theta greater than, I'm going to call it critical, theta c. There's my theta, and here we've got our theta, so theta is less than theta c. Okay, and that's it. If it's neither of those, if it's actually on a certain angle, then it will neither escape out of the solid material or the denser material into the thinner media. Sorry, so denser material media into the thinner one. If it's bigger, it will stay trapped within the denser material. Now, can we prove that? Yes, we can. So a little bit of maths to go with it, and it's a very simple idea, all based on what we did last lesson. So, what we can say is, using that equation from last lesson, nu1 sine theta 1 equals nu2 sine theta 2. Okay. At the critical angle, if theta 1 is the critical, is at the critical angle, I'm going to call it the critical point, okay, theta c, then according to that diagram, it's not getting out, it's not staying in, so we're going to say that theta 2 equals 90 degrees. Okay, so that's the maximum theta 2 can be before it can no longer escape, and so it's trapped inside. Now, what that means is we can put that all together. So if we were to say, if we just put that into the maths, then refractive index 1 sine theta c, okay, that's putting that in there, will equal refractive index 2 times by sine of 90, which is of course 1. Okay, so what that means is we can end up with a rearranged equation that is more useful to find theta c. So simply it's a ratio of the second material over, the refractive index of the second material over refractive index of the single one of the first one. If you're going into air, so if second material, is air, then the refractive index 2 is just simply equal to 1. Okay, so that means that it's travelling at the speed of light. So that can simplify to critical angle sine equals 1 over refractive index of the material that it's in. Okay, so that's only if it's in, make that clear, in air or a vacuum. Difficult to do in reality. So we can work out that angle, but more correctly it's this one here, because it depends on what's surrounding it. And this is where it gets really kind of useful. So what we can do is, I'm sure you did a little bit at GCSE, we talked about the cladding, we talked about fibre optics or optical fibres, and what they were was a way of transmitting light to carry signals, amongst other things. Few advantages here. Light frequencies are much, much higher than electrical frequencies, and so AC frequencies, so they can carry much more information. But we can also use them to literally shine light about, and you get endoscopes. Now, in the old days when I was a kid, with radio, radio waves being produced by electrical currents means that when you were talking on the telephone, sometimes you pick up someone else's conversation. Light, if you put two glass rods together, so glass fibres carrying signal, well, it could jump from one to the next as anywhere that they touched. So what you need to do is you clad them, but the cladding is not to protect them. It is a little bit, but it's not mainly to protect them and mainly to keep the signals inside. What it is designed to ensure that you get a better signal coming through. If you were going to send a binary signal, I'm sure we got all a rough idea of that. If you'd send in just say a whole series of ones and noughts, so 0, 1, 0, 1, 0, etc., etc. So if you were to send that along as flashes of light, turning on, turning off, turning on, turning off, what you'll find is by the time it gets to the other end, you're hoping to get the same signal. But if some light zigzags, it's got a lot further to travel than one that goes through the middle. And so what you start to get is, depending how far they travel along, different frequencies and different parts of signals travel at different speeds, and you end up with basically the pulses, in this case, merging into rounded different things, and you start to basically get noise. The zeros disappear, the ones drop down, the zeros rise up, and it's very, very messy, and you can't tell what's going on. Okay, so those series of pulses all kind of merge, you lose your signal. Okay, so what they do is they will make sure that ones that are going too much zigzagging, okay, so they're not paraxial, they're not parallel to the axis down the middle, will make sure that actually they get trapped in the cladding. Okay, so going back off here, it might sound a bit mad, the black cladding does actually let light go through the light wavelengths that are used. So often infrared, because glass is a bit clearer for infrared than it is for visible light, passes through much faster. If we do that, the black cladding does let infrared light through. However, it lets it through more easily than the core, which sounds a bit mad, but that's effectively putting a thinner media around the outside, and to fit in with this, the smaller that is, the better the angle. Okay, so let's take some examples. If you had optic fibre where the core, okay, better put that in, the core is 1.5, so fairly standard glass. If we surrounded it by air, then using our maths from up here, we've got refractive index 1 sine theta critical equals 1 times sine 90, which equals 1. So effectively, if you put that in, the critical angle theta c will equal 41.8 degrees, which means that anything up to 48 degrees could still, anything over 41.8 will bounce back and forth. That's quite zigzaggy, yeah? So what I can do is change it. So if we did this one, then what we can get for this material is by surrounding it on the outside, and again using, that's your material 1, I should say. If you put that in, then what you'll get is the critical angle will equal 69.0 degrees. Okay, so actually that's much flatter. Rays beyond that angle will get bounced along, but anything less will get escaped out the side, will let shrink out the side. Okay, so if we take it a bit further, so if we actually make the outside slower than 1.5, so we put that in 1 sine theta c equals 1.6, well, what you'll find is 1.6 divided by 1.4, second function sine theta c can't be calculated. Okay, it's an impossible number, i.e. it won't occur. Total internal reflection is impossible. So you need to have the thinner media, the lower value media on the outside. You cannot have internal reflection on the outside of a dense substance. Now, there's a little bit more in the notes, okay, which is worth reading through. It brings you some extra ideas, and I'll explain them more in the lesson. But there's different ways of changing it. So we got some really, really clever kind of systems. We've got monomodal fibres, which only let that single mode, i.e. straight rays that go down the middle all the way along to the ends. The problem is, as soon as you bend that, you get the same effect. Multi-mode is the one that we've just talked through, where you could go very zigzag, could go straight, and you could go anywhere in between. But a very clever one is using graded index. So this is rather like a whole series of slowly changing refractive indices dropping as you get closer to the edge. So on our graph here, maximum refractive index in the centre and fading away until you get to that shielding around the edge, okay, that cladding or sheath. And so what happens there is, because of that, anything that goes a bit odd will actually curve and straighten up. So it's a self-correcting system as well. Other ways around it we can, as I said there, limit the data transmission rate, so you could send less bits per second so they don't mix up. Not very helpful, because you actually want lots of information, more and more information with the complex world that we live in now. So something like that, or that works better. But what you can also do is experiment with different shapes. So if you go back to there, for example, electronic engineers don't actually transmit it like that. They transmit what's called solitons, and they look a bit like that, more clear than that, but they actually self-correct as they travel along. So lots of clever stuff, but yeah, big idea. The main idea is optical fibres in communication, and that's why it's so important nowadays. Without this, we wouldn't have broadband. Okay, so your Wi-Fi actually is a slower data rate than through cable, but cable is what actually drives the system. So to get to your modem, you've probably got electrical signal from that nearby box, but from your nearby box where your endo fibre optics are, you'll get a short electrical link, and then you get your Wi-Fi. So it's slowing down the transmission rate as you get more and more close to your home. However, the main system around the country is through fibre optics. Okay, let's leave it there.